second part we will discuss is graphical representation of S. In this graphical representation, we will represent the variation of the displacement with respect to time. Now, we will consider a special case. Suppose that the particle starts its S.H.M from the mean position, that is at t is equal to 0, x is equal to 0. And the particle is supposed to be moving towards the positive state. Then under these conditions, the displacement equation of the particle is given by x is equal to a sin omega. So the displacement is sine function of omega. So variation is sinusoidal variation. The curve representing variation of the displacement with respect to time will be a sine curve starting from the mean position or starting from the origin of the coordinate system. If we select the coordinate system with the x-axis representing the displacement of the particle, representing the phase angle R, and the displacement is represented along y-axis. So this is amplitude on the positive side, capital A, this is minus A. If we consider phase angle along the x-axis, then it will be omega t equal to 0, pi by 2, pi, 3 pi by 2 and 2 pi. So that when particle starts its S.H.M from the mean position at t is equal to 0, x is equal to 0, is the sinus. If we represent the graphical representation of x with respect to t, then instead of this omega angle, this is t by 4, t by 2, 3t by 4 and capital. So this is the graph which represents the variation of the displacement with respect to time. We can have the chart for the different values of the x for different instant. 0, t by 4, t by 2, 3t by 4 and capital. Omega will be 0, pi by 2, pi, 3 pi by 2 and 2 pi. X will be 0 plus a, 0 minus a, 0. These are the values of x for the different instant of omega t or for different instant t. From this, the displacement x will be 0 at mean position and at extreme position x is equal to plus or minus. So this is the graphical representation of the displacement with respect to phase. The second curve which can be plotted representing variation of the velocity with respect to time or phase angle. The equation for the velocity v is equal to a omega cos omega. Then particle starts its S.H.M from the main equation. At t is equal to 0, x is equal to 0. Then x is represented by a sin omega t, and differentiating this equation we can write v is equal to a omega cos omega t. Similarly, for the different instant at t is equal to 0, omega t equal to 0, velocity will be a omega 0 minus a omega 0 a omega. If we plot a graph which represents the variation of the velocity with respect to time by taking time along x-axis and velocity along y-axis, then this term represents a omega and this is minus a omega. The instantaneous values of the velocity are at t is equal to 0, x equal to a. Then at t by 4 it is 0, at t by 2 minus a omega 0 minus 1. This variation is represented by one again a cosine function, or this is cosine. So, at mean position, that is at x is equal to 0, v will be equal to a, of course plus or minus 1. In magnitude, it will be O. At x is equal to plus or minus a, that is at either extreme position, the velocity will be g. The third graph, which shows the variation of the acceleration with respect to time, can be plotted by considering the equation for the acceleration a equal to minus a omega square sin omega. When the particle starts its position from the main position, the displacement x is represented by x equal to a sin omega t. The different values of the acceleration at different instants can be calculated by putting the different instant values of the t in this equation, and these will be acceleration a will be 0 for omega t equal to 0. It is minus a omega square for pi by 2 sin omega t equal to sin pi by 2 plus 1. So a is minus a omega square 0 a omega square 0. So the third graph, which represents the variation of the acceleration with respect to time, can be plotted by taking time along x-axis and acceleration along y-axis. So these different values of the acceleration are 0 minus a omega square, 0 plus a omega square, and 0. So this is the curve. If we join these points, this is 1 second sinusoidal. So we can conclude at mean position, that is at x equal to 0, acceleration will have minimum value and it is equal to 0. At x is equal to plus or minus a, that is at either extreme position, acceleration will be equal to a omega square magnitude, that is the maximum value of the acceleration. Similarly, we can draw the different curves showing variation of the displacement, velocity, acceleration with respect to time when particle starts its Ch-M from the positive H position. From this curve, we can conclude that the phase relation between the x, v and the acceleration if we look at the phase angles, at t equal to phase angle of the displacement x is sin omega t, that is phase angle omega t. In this case, the phase angle will be equal to omega t plus pi by 2, and this is omega t plus pi. So we can conclude from these two equations that there is a phase difference of pi by 2 between the linear displacement and linear velocity of the particle in unit system. And linear velocity leads the linear displacement by a phase angle of pi by 2. Right? Because the phase angle is omega t for x and it is omega t plus pi by 2 plus pi for the v. So this phase angle is additional, has pi by 2. So this is lead by a phase angle of pi by 2 with respect to omega. So velocity leads the displacement by a phase angle of pi by 2, or we can say that the displacement x lags behind the linear velocity by a phase angle of pi by 2. Once again there is a phase change of pi by 2 or phase difference of pi by 2 between the velocity and acceleration. And in this case, acceleration has phase angle omega t plus pi, where velocity has phase angle omega t plus pi by 2 at given instant t. So this is the phase difference of pi by 2. And in this equation, this phase of the acceleration is higher by pi by 2. So in this equation, from these equations, we can conclude that the linear acceleration leads the linear velocity by a phase angle of pi by 2. Or the velocity, linear velocity lags behind the linear acceleration by a phase angle of pi by 2. If we consider the linear displacement and linear acceleration, then the phase is omega t at instant t for the displacement and phase is omega t plus pi at instant t for the acceleration. So the phase omega t plus pi and phase omega t differs by a phase difference of pi. So there is a phase difference of pi radian between the linear displacement and linear acceleration. And we can say that the linear acceleration leads the linear displacement by a phase angle of pi radian, or displacement lags behind the linear acceleration by a phase of pi radian. And this phase relation is true no matter particle starts its displacement from any position. For all positions, this phase relation between the x, v and t are. So if second type of the variation we will conclude in short, if particle starts its S.H.M from positive x, then alpha will be equal to pi by 2, and the equation for the displacement is x is equal to a cos omega t. The variation is represented by at t is equal to 0, x is positive. This is the variation of the displacement with respect to time when particle starts its acceleration from the nucleus. If we take these points as a omega, this as minus a omega. For the velocity taken along y-axis, we can draw another curve for the displacement as v is equal to a omega sin omega with negatives. So this is starting from v a omega equal to g. So g minus a omega 0. This is the variation of the velocity with respect to time when particle starts from positive acceleration. Similarly, for the acceleration, by taking equation, acceleration a equal to minus a omega square cos. By taking this equation, this is the formula for the acceleration with respect to time. In short, the graphical representation of the S.H.M, when we consider the variation of the displacement with respect to time, or velocity with respect to time, or acceleration with respect to time, the curve will be either sine curve or cosine curve. Now, one more variation we can discuss. We have discussed the graphical representation of the between acceleration and displacement. We have discussed x is equal to a sin omega t or x and t, v and t, acceleration. In the last period, we have discussed the variation of the velocity and the displacement. Now we can represent the variation of the acceleration and velocity. The equation for the acceleration as minus a omega square sin omega t plus alpha, and velocity as a omega cos omega t plus alpha, with assumption that x is equal to a sin omega t plus alpha. Assuming this equation for the displacement of the particle, we can obtain the expression for the velocity and linear acceleration. If we rearrange these equations, we have sin omega t plus alpha t is equal to a divided by, of course, minus a divided by capital A into omega square, and cos omega t plus alpha will be equal to v divided by a omega. If we square and add these two equations, we have equation a square divided by capital A square omega raised to 4 plus v square divided by capital A square omega square is equal to 1. That is sin square omega t plus alpha plus cos square omega t plus alpha will be equal to 1. And this is the equation of the ellipse. So the variation of the acceleration with respect to velocity represented graphically by taking velocity along x-axis and acceleration along y-axis. This is a omega square minus a omega square. This is a omega with negative sign and a omega with positive sign, velocity. So this equation will be when the velocity of the particle is maximum, that is at mean position, the displacement is 0. When the velocity of the particle is minimum, that is 0, the acceleration will be maximum. And if omega is equal to 1, then this ellipse changes to circle. So the graphical representation of the acceleration with respect to velocity for a particle performing the linear escape with unit angular velocity, the graph will be a circle. So representation of the acceleration with respect to velocity. So in this way we can discuss the graphical representation of the different parameters like velocity, acceleration, displacement with respect to phase angle or with respect to each other, say acceleration and velocity, acceleration and displacement, velocity and displacement, and so on.